Ladies and gentlemen, now we start our conference, and let me introduce the first keynote lecturer, Professor Ying Liufu from Lanzhou University, with his keynote lecture, Improved Neurodynamics Models for Real-Time Nonlinear Optimization with Applications. You are welcome.
Okay, thank you very much. Thank you the invitation from Professor Eugene and Professor Project also. Thank you for the introduction of the Professor Eugene. And today I want to share you about the recent work I have done, and the title is the Improved Neurodynamics Models for Real-Time Nonlinear Optimization with Applications. And I will discuss it from three main parts. And first of all, the object we focus on is the time-varying optimization, which means that the variables and objectives and constraints are evolving with time. Solving time-varying optimization is an important foundation in many fields of science and engineering, including robotics control, autonomous vehicles, and multi-agent systems, and fail to consider the time-varying characteristic may lead to accident, maybe. And in 1986, Hopfield found that the neural network can solve the traveling salesman problem in parallel. This research promote a computational paradigm, namely the optimization problem solving models based on the neurodynamics or say neural network. From 1996, Professor Wang Jun has made significant contributions by establishing a comprehensive set of theoretical analysis and modeling methods for neurodynamics optimization and its applications. Essentially, neurodynamics is a powerful tools for solving the real-time nonlinear optimization, which can take the equilibrium point of the system corresponds to the solution of the optimization problem. Also, it can take the neural network corresponds to the dynamic system. So the neurodynamics has been developed for many interesting applications. For example, task assignment is an important part of multi-UAVs cooperative mission planning, and it also the premise of the realizing UAVs cooperative combat. The UAV competitive cooperative distributed control technology combined with neurodynamics model can calculate the best control scheme in real time. And moreover, with the help of neurodynamics methods, the potential structural inaccuracy problem can be overcome by the robot learning algorithm based on the nonlinear optimization of neurodynamics methods. Furthermore, robots based on real-time nonlinear optimization control are widely used in important fields such as national important industry, medical service, and so on. And neurodynamics methods is an important tool for solving time-varying optimization effectively. And on this slide, I will introduce the existing work and limitations of conventional algorithm in solving time-varying nonlinear optimization problems. And traditional algorithms are typically designed for the static problems, relying on the assumption of short-term time invariance. However, when dealing with the time-varying nonlinear optimization problems, this assumption can lead to significant lagging errors. And this table lists several representative conventional methods, including gradient-based neural networks, general projection neural networks, and primal dual neural networks, and Newton-Raphson iterative methods, and modified Newton integration methods. And why these methods have theoretical advantage, such as solving optimization through error functions or objective functions, they often fail to respond efficiently to dynamic change in real-world applications. And these limitations raise an important questions. How can we design more efficient models with stronger real-time adaptability to handle the time-varying characteristic of optimization problems? And this question sets the stage for the subsequent research and improvement I will present. And the important problem we focus is how to solve the time lagging error in solving time varying optimization problems. And to overcome these issues, my work proposed a novel speed compensation neurodynamics model. And this model breaks through the short-term invariance assumption of the traditional algorithm. Is designed specifically to handling the time-varying nature of the optimization problems effectively. And actually, it introduced dynamic adaptability to respond to real-time change in the optimization landscape. Below, you can see how the problem is modeled mathematically, and with the optimization function incorporating time-dependent variables. The neurodynamics approach represented here is used to adapt to the change over time. On the right, I will introduce the error function, which is the central to the performance improvement of this model. And the flowchart at the bottom further illustrates the structure of the proposed neurodynamic system. And through this combination of the problems, modeling, and neurodynamics, my approach provides a systematic and effective solution to the time-varying optimization problems. And I compare the performance of conventional models with proposed neurodynamics models. And on the left side, the comparative model shows a lower bound of the error convergence, as it fails to fully utilize the time derivative information. And this limitation results in the residual errors as depicted in the in this diagram. And in contrast, the proposed neurodynamics methods achieves zero convergent error, as shown on the right side of the slide. And the error function approach to the zero over time, and it demonstrates the effectiveness of the proposed model in solving the time-varying optimization problems with higher precision. And in this slide, I present a specific optimization problems and its constraints. And as shown on the left, the problem involves a complex time-varying objective function with multiple variables and dynamic constraints, making a challenging scenario for conventional methods. And on the right, the convergent errors comparison demonstrates the performance of the proposed neurodynamics, named VCRNN model, and versus the general gradient neural network named GNN. Why the GNN exhibits significant fluctuations and residual error, and our proposed VCRN model quickly converge to near zero error, maintaining stability and precision throughout the whole process. And this slide shows the variables behaviors under equalities and inequalities constraints. Even for the time-varying cases, maintaining stability and precision. In contrast, the GNN model failed to satisfy the inequality constraint and failed to satisfy the inequality constraint. And these results demonstrate the proposed VCRN models superior constraint handling and adaptability in dynamic optimization scenarios. And in these slides, it demonstrates the applications of our model to motion planning for redundant robots, and comparing the results of the proposed neurodynamics with conventional models. Yes, and on this slide, our proposed VCRN models generate smooth and stable trajectory and satisfies all the constraints effectively, and the motion is precise with the minimal error and oscillation. And the comparative model fails to satisfy the constraint, and leading to unstable trajectory and significant fluctuation. And this error highlights the limitation of the comparative models in this dynamic robotic task. And the whole experiment clearly showed the superior performance of our proposed model in achieving accurate and stable motion planning for redundant robots. And this slide introduces the second job of our research, and this slide introduced the limitation of the conventional algorithm when applying the KKT conditions in solving time-varying projective programming problems. On the left side, we can see the optimization problem defined with equality and inequality constraints. When the KKT conditions are applied, auxiliary variables are introduced to satisfy these constraints, but it will introduce two others variables, and it will lead to a higher dimensional of solving models, and further significantly increase the computational complexity. And this process also involves defining error functions, and further this is the metric definition of the error function. And by utilize this evolution formula, we can further obtain the finally zero neural network models. And this model can be finally utilized to solving these TVQP problems. But I introduced here and this work is a very traditional models to solve the TVQP problems, and it will incur some computational complexity problems. And in And my work here outlines the research roadmap of my work, focusing on solving the multi-set constraint optimization without relying on the KKT conditions. Instead, we use a projection-based approach, and on the left, the problem is modeled as a multi-set constraint optimization problem, which ensuring the feasible solution by projecting onto the constraint set. And the central section introduced our modified gradient projection neural network, which directly handle the constraints using the projection operator, avoiding the computational burden of auxiliary variables in KKT-based methods. And on the right, practical applications of our approach is demonstrated with the portal crane control scheme, where the projection methods ensure the stability and precision in motion control. And this slide shows the MSCO problems, which involves optimizing functions subject to multiple compressed constraints. And the problem formulation is shown in the center, highlighting the constraints such as box constraints, superball constraint, and super ellipse constraint, each depicted in the lower part. And this constraint represents diverse feasible region, enabling flexibility in addressing real-world problems. However, there are few available solution methods can figure out the MSCO problem sufficiently and effectively for the time being. And one of the reasons is that in the existence of these complicated multiple set constraints, and in response to this requirement, inspired by the gradient-based neural network and the orthogonal projection theorem, and we propose a modified gradient projection neural network. Its principal gist is to project the gradient descent orientation of the optimized objective function onto the multi-set constraint, and thereby we can assure the descent direction of each iteration within the feasible region. Therefore, as the solution progress goes on, the optimal solution to the MSCO problems can be definitely found under the premise that the convexity of the objective function. And most importantly, our proposed MGPN model can solve the MSCO problem directly without previously making the complex transformation to the optimization problem, which is quite different from the existing neural dynamics methods. And the right side of the slide is the pseudocode of the proposed MGPN model. Yes. And in this slide, we conduct two numerical examples, of which the results are accessible in the slide. And for the first example, as seen on the top of the slide, the proposed method is comparable to the counterpart Rn, and in the convergent performance, the figures on the bottom of the slide, describes when the optimization constraint by multiple set our proposed MGPN models can also well figure out it and finally reach the required optimal point. And furthermore, we apply our models in dealing with the portal under actuated crane control problem, and experimental results solve us with a good performance. And the given butterfly tracking task by pendulum is well accomplished. Most importantly, the constraint on the input force are strictly satisfied, and the tracking errors are small enough. On the other hand, as to the counterpart methods, the tracking performance are somehow disappointed under the same experimental setting. And constraint on the input force are slightly broken. Accordingly, the tracking errors are relatively larger than that of the proposed model. And by the way, we make an animate on the Simulink platforms. Yes. Notice that the pendulum can quickly stabilize after the control, which is beneficial to the real industrial scenarios in factory to guarantee the safety of the operators or other workers. Yes, and the pendulum quickly stabilize after the control. Yes. And the third part of my work is presented here, and the problem description. First, we goes to the problem description. As we can see on the slide, the research roadmap of this work is exhibited. At first, the left side part presents the general time varying equality constraints optimization problems, and in the middle part, we tactically design adaptive, noise tolerant differential neural solution to solve this problem. And finally, the experimental result on the redundant robot further demonstrates our effectiveness of the proposed model. And at the upper part of the slide, we can see that the proposed adaptive noise tolerant differential neural solution model consists of two main parts. And the first one is the conventional zero-ring neural network, and the second part is the weight adaptive part. Notice that the weight adaptive part may compensate for the first conventional ZN models that is exploited by the noise. By interacting with each other, the time-dependent equality constraint optimization problem can be effectively solved under the noise circumstance. And the right side part is the shortcut of achieving our ANDNS model. For comparison, we presented two traditional recurrent neural network, which has been proven to be effective in addressing the time-varying system by many scholars. Of course, they have some merit. However, they also go through some shortcomings. First of all, the OZNN models behaves with high efficiency in time varying system and have a simple model structure. But unfortunately, it is vulnerable to noises. As to the noise-tolerant recurrent neural network, which is designed by Longjin and published in TAC in 20,000 and in years ago. These models have overcome the drawback of the OJA models, and it can handle the noises with the integral terms. The NTL models can theoretically eliminating constant noises, and meanwhile boldly restrain the linear noises. However, it is inferior in high-order noises. Different from the above-mentioned methods, our proposed model inherit the effectiveness and rapidity of the traditional zero neural networks to solve time-varying problems. And the second point is that we introduce a weight adaptive structure to adaptively eliminate the noise disturbance of the original models. And the third point is that a new perspective of disturbance elimination in recurrent neural network is developed with higher accuracy and robustness. And here shows our model structure of the proposed models, and clearly, and it has a weight adaptive mechanism to learn the noises from the noise disturbance in the zero neural dynamics models. And also, we also conduct some experiment to support our claim. And the first experiment is conducted with some time-dependent parameters has been posted on the slide. Let us notice the first figures on the right side. We simultaneously start the solution process from 10 different initial states, and the generated residual error, and of course the corresponding solution state had also coincide with the theoretical solution, and the residual error quickly converge to zero also. And moreover, to demonstrate the robustness of the proposed model, we injected different noise into the proposed model compared with the existing model. The proposed model can always conquer the noise conditions and achieve the best convergent accuracy. And the comparative models, including GNN and OJNN, VPNN, and NTJNN models, and they fail to behave a good performance while handling these three types of noises. And this slide highlights the effectiveness of our proposed model in suppressing harmony noise during the motion planning of the redundant robot. And on the left side, the proposed model generates smooth and accurate trajectories even under the noise conditions, maintaining stable and precise trajectory throughout the whole process. And on the right side, comparison with VPNN and OJNN models shows that these two methods can these two models shows that is they cannot restrain this significant disturbance from the harmonic noise circumstance, resulting in unstable trajectory and increasing errors. And this experiment result demonstrates that our proposed model is highly robust against noise interference, providing reliable performance in dynamic and noisy environment. Likewise, in the practical application, we accomplish the same control effect with the simulation we conduct on the last slide. Now we come to the future work part. And for the future research, we aim to develop collaborative neurodynamics optimization methods that combines the strengths of neurodynamics and swarm intelligence, forming a hybrid intelligent approach. As we all know, neurodynamics is a brain-like nonlinear dynamic system. It excels at local search, but tends to get trapped in the saddle point. The swarm intelligence methods demonstrate strong global search capabilities, but lacks a complete theoretical foundation. By integrating the local research, the local search ability of the neurodynamics model with the global search ability of the swarm intelligence methods, we can create a hybrid framework to tackle some challenging non-convex optimization problems more effectively. And example 1 and example 2 demonstrate the test scenarios where combining these strengths can significantly improve optimization result, overcoming limitation of individual methods. And this approach holds great promise for solving complex real-world optimization challenge, especially in non-convex optimization scheme. Of course, we have already conducted some exploratory work and design robot collaborating neurodynamics model to address the nonlinear optimization problems. And on the left side, and the neurosolvers framework combines neurodynamics models with a co-evolutionary mechanism. It guarantees the convergence with probability 1, leveraging the rules and that incorporate local and global search capability. And on the right side, algorithm 1 demonstrates a robot co-evolutionary neural-based optimization approach, where agent perform local search guide by the neural dynamics we propose here, and we can find the global optimal point by using the swarm intelligent search algorithm. In the future work, I will conduct two interesting application including the non-convex optimization problem for positioning techniques. And in noisy environments, positioning techniques often have rely on other devices or methods to withstand the disturbance. And our proposed model based on robot evolutionary neural models can reduce the influence of the perturbation and obtain the global optimal solution. And another research is that the non-convex optimization control for autonomous vehicle, and in the control system of autonomous vehicles, due to the and it faced the challenge from highly nonlinear dynamics and often getting trapped in some local minima. And this can deteriorate control performance, especially in some obstacle-rich environment. And the research on the probability neurodynamics models can handle these cases. This illustration showcase a simulation scenario with obstacles, potential fields, and optimization landscapes, and demonstrate the importance of develop some advanced models for the non-convex optimization control and for the autonomous vehicles, and to safely and smoothly navigate in the real world scenarios. Okay, the above is my whole speaking, and thanks for the invitation by Professor Eugene and Professor Project. Thank you very much.
You are welcome. Thank you very much for your presentation.
Okay.
Now it's time to ask questions. Dear colleagues, who would like to ask?
Okay.
Okay, maybe I have a couple small questions just for understanding. So in this neural networks, you have like weight coefficients, yes? Like in classical neural network.
Yes.
Do you have? Okay, so how do you tune these coefficients? With gradient descent or?
Do you mean how to set the coefficient?
How to train the neural network?
How to use my neural network?
No, how to train, how to learn the coefficients.
Training process, how is it organized? Training process.
Okay. Okay, I will find the structure of one of my work. You mean how to tuning the performance of my neural network?
Yes.
Yes.
Yeah.
Okay. Actually, the key point of tuning the performance of our neural networks is to guarantee the coefficient like mu, which we have to guarantee the mu is large than 0, and we can guarantee the convergence of the of these neurodynamics models. I don't know. Whether I answer your questions.
Yeah, I think I understand it better. So it is different from the training of classical neural networks with stochastic gradient descent. So it is different.
Yeah.
I see. Okay,
Yes,
thank you.
yes. Okay.
Any more questions, dear colleagues? You are welcome.
First of all, thank you for your presentation.
Okay.
My question is, in your optimization problem, variables, objective function, and constraints depends on time.
Yes.
If your problem becomes static, can your approach solve static problem?
Do you mean if my problems get stuck?
Yes, static
Get
and
stuck,
don't change over time.
or no change, or no change with time? Yes, I understand your questions. And let me. Yes. Actually, the problem we discussed in this research is that our coefficient matrix is evolved with times. Yes, the matrix is involved the time, and of course, if we have nothing to do with the metric, if the metric is not is irrelative to the time, it will reduce to the stationary problems, and it is the one specific case of the time varying cases. So our proposed model can also handle this stationary optimization problem too. Yes.
Okay, I just see some derivatives with
Yes, some derivative here. Yes.
and I think some derivatives becomes equal to zero because time
Yes.
don't influence the result.
Yes. The derivative converts to zero means our proposed model eventually find the equilibrium point of the system. It further means that the solution of the optimization problem can has been found. Yes.
Thank you again.
Okay.
Sorry. Who has another question? Please ask. Okay, no questions. Well,
Okay.
thank you very much for your presentation and answer our questions. You are welcome
Okay.
for our next conference.
Okay.
Again.
Thank you very much for this invitation. Yes. Thank you, Professor Eugene Semenkin.
You are
Thank you
welcome.
again. Okay.
Okay.